I'm the only one from North America here? All right. Well, you know, it's been a tough couple of years, of course, for all of us. This is my first trip overseas since the pandemic started. I'm sure for many of you, it's our first big meeting. So it's such a thrill to be here this weekend and to spend time together. I know the numbers, of course, aren't as much as we're used to doing, but the numbers aren't what's important. It's, of course, the quality of being together and sharing knowledge and sharing information. So it's really wonderful to be here together. And we're going to get the program started. It's really a pleasure to be here. I've been working with VSY for the last many months. Very fascinated with the technology, wasn't fully aware of what the technology can do and how it works, but as I learned and used and got more experience with you know, the optics and the design and the attention to detail, very excited to share with you the concept. And I will be starting talking about the golden ratio, which is something that maybe many of you have seen in art and in the world as well today. And with us here we have Dr. Ike Ahmed from Germany, from Dusseldorf, and his partner, Dr. Carsten Klabe. I just heard, actually, if you translate their names, it's cream and cookies. So those of you like cookies and cream, you're in for a treat. I'm not sure what Ahmed you know, translates to. I don't know, but
as long as you don't call me Cookie Monster.
Okay, we won't call you Cookie Monster. So if we can get my first slides up, and we thank again VSY for putting this together. I'm not sure who can put my slides up. Here we go. This is the technical side of it. So I'm doing an introductory talk. And my talk is to speak about the new Trinova Pro and the technology behind it. I'm not sure how many of you have heard of sinusoidal diffraction, but I'm going to share some thoughts around this, and I'm not sure how familiar you all are with the golden ratio. Now, these are my disclosures. I apologize. I do have a bit of a tendency to make many friends in the business, but this allows us to really continue and to innovate together. Now, we all know, we're here at ESCRS, we know even since before the pandemic, but certainly during the pandemic, how the visual needs of ourselves and our patients have evolved. I mean, we're in a digital world. We're typically working intermediate and near at great lengths, whether it's computers or tablets or cell phones. And even those maybe we don't think are, for example, our grandparents and elderly, are all into this era here. Now, this makes it complicated. There's always a balance in picking the right presbyopic correcting lens and meeting patient expectations. It seems like we're always trying to balance out the increased range of vision, but what happens when we manipulate light, potentially we have some risks, and those risks include contrast sensitivity loss and halos and glare. And for these two reasons alone, many of us have been reluctant to really offer these technologies for a wide range of patients. Well, of course, we're all looking for that masterpiece. We're looking for that perfect arrangement of technology to really address and balance these needs. And I think we have some better answers today, and I'm going to share with you. This is probably best summed up in what's termed the golden ratio, and we're going to call this the golden ratio in IOL technology. How many have heard of the golden ratio? Put up your hand. Okay, a few of you have. Well, of course, if you're inspired by the paintings of Da Vinci and Dali, if you've seen what the ancient Romans have done, and the ancient Greeks actually were the first to identify the beautiful asymmetry that occurs in nature with plants, with trees, with insects, with snails, and translated that into art, into architecture. And really, the golden ratio is really a ratio of proportions. It's a bit more complicated than that. It's a mathematical equation, the Fibonacci sequence of numbers. Don't worry, we're not going to go into a math lesson here. But the ability to capture that beautiful natural asymmetry, which is what really is captured in these pictures, is what this is about. And so for my section here, I'm going to speak about masterpieces. Okay, the three masterpieces I want to share with you today. The first one is the Great Wave of Kanagawa from Hokusai. This is one of the most popular and well-known Japanese arts of the Great Wave. Mount Fuji is in the background. Now, what is it about waves? Well, in ophthalmology and optics, we always talk about waves, right? Talk about wave and particle theory of light. Well, of course, in multifocal technologies and other technologies, we use diffractive gratings and obstacles to bend waves, to bend light. And the concept is waves. And you see, of course, diffractive gratings on different lenses. But every diffractive grating is not the same. And perhaps that's something we were all taught, but they're not the same. The idea is, can we create a better diffractive design, a better surface? And this is the sinusoidal diffraction technology. Let me start on the left here. Here you see the classical blaze or sawtooth diffractive pattern. Notice the sharp edges. This, of course, does create bifocality. It also creates 0 first and second order wavefronts. And these potentially can also cause scattered light and dysphotopsia and loss of contrast and transmission. Remember that point. It's very different with the gentle sinusoidal diffractive pattern you can see here, with the -1, 0 and the first order wavefronts here. A very different type of modulation that you'll see how the Trinova Pro does this. And I think it's very fascinating when you think about it. I didn't realize the different ways to consider diffractive gradients. Here's an example of a traditional trifocal. You can see the sharp edges here lined up on the surface of the lens. And if you look at the difference if you look at the difference in the sinusoidal gradient, can I get the next slide, please? I think I'm stuck on there. Here we go. Oh, back one slide. If you look at the previous slide here, you can see that the diffractive gradient is very different. The smooth surfaces are identified on the surface of the optic here, you can see. And this is different than the sharp edges. The problem with these sharp edges and the typical blaze or sawtooth is we have some loss of light with the second order wavefront. What does this do? It means there's less light transmission that occurs in this lens and dysphotopsia. Two issues that make us concerned about multifocality. Next slide. Okay, so here's an example, a more focused example on traditional sawtooth diffractive multifocal. You notice the 6 rings here. This does provide a broad range of vision, we know that. But we lose some light. We're down to about 88% maximum light transmission. That's all we can get from the lens. And this can create glare and halos, of course, and contrast loss. On the other hand, what we're going to show with the sinusoidal pattern, which I think is brilliant, we have less loss of light. It's actually 93% transmission, which is close to the natural human lens. This reduces the issues around halos and glare. It improves contrast sensitivity. Again, the two areas we're trying to address. So go and learn about sinusoidal diffraction. This is all around us in nature. We all know, of course, the sine wave. We see it around us. It's not raining today, but if it was raining and you looked out into the canal on one of your boat cruises, you'll probably notice sinusoidal diffractive waves are all around us. Let's look at the specific profile of the ridge of the sinusoidal wavefront. What you'll see is that the different parts of the ridge contribute to the different focus distances. You see here on the outer part of the ridge is the near focus. On the inner part of the ridge is the far focus, and the whole surface contributes to the intermediate. We can tune this to the amount of energy delivered for each of these foci point, which I think is very, very clever. We all know on the left the regular sinus, normal sinus wave. This is basically an equal proportion, as you see there, 1/3 toward, for example, far, 1/3 intermediate, 1/3 in near. But the secret sauce in what the Trinova has done is optimizing the amount given to each proportion. This is an example here. For example, far can be 0.44, 44%, 20% intermediate, 30% near. And this optimization that really harnesses the ability for continuous vision and reducing side effects. And I know that my colleagues will speak more about the basic data and also the clinical results as well. This is just a confocal 3D microscopic view of the surface of the lens. You can see the nice gentle sloping. There are no steps here. There are no steps that we typically see with traditional lenses. It's nicely shown in this example as well. Well, we all want to know how this lens performs clinically. This is a theoretical bench testing. This is a defocus curve. We always look at defocus curves when we think about the performance of a presbyopic lens. What we want to see is a flat top. We want to see basically continuous range of vision, 20/25 or better, which is what we're seeing here at far, intermediate, and near. And you can see again that despite the fact that we are moving light around, we retain a high degree of focus as seen in this example here. So mathematical patterns, whether it's the great wave or whether they're wave fronts on a diffractive lens, really set the stage for a masterpiece. And when you look closely, you can see the golden ratio in their masterpiece from Hokusai. Well, let me talk about the second masterpiece, and this is the Mona Lisa. We're all familiar with the Mona Lisa, of course. And Da Vinci was brilliant, right? This was one of the first portraits that were done with a sitting individual with a background that was imaginary, using aerial visualization, using light to show a sundown here with Mona Lisa looking toward a sundown. You can see the image from in the background here. And really the use of light and colorization was brilliant in this time and remains one of the most important masterpieces of all time of art. Well, speaking of light, we know how important it is for the performance of a lens. Here's some examples of other type of multifocal lenses which do fairly well, but we all aspire to lose as much light, as minimal light as possible. You can see on the left, you see what we typically see in a natural crystalline lens. And the Trinova here is, again, very close to that. But it's more than that as well. It's also how does this perform in mesopic and scotopic conditions. Pupil adaptiveness, I think, is very clever. A small pupil, we have a really good depth of focus. We may not need to really have as much light distributed, for example, to the intermediate zone. On the other hand, when we have larger pupil, less accommodative demand, and night vision, we may want to shift light more toward the intermediate foci. And as you see here, we have excellent distribution to distance throughout all different pupil sizes. And the dotted line is near, you see an increase near as you get in the 3 to 4 millimeter pupil, and then it drops down in scotopic conditions, while intermediate goes up. This is a very clever way to allow us to distribute light energy, again, with these focus points. Again, light and the golden ratio really contributes toward this masterpiece. A lot of it is mathematics, and as you can guess, the third masterpiece that I've just shown you here is the Trinova Pro, which is a brand new lens and a new platform, which is just being released here, and the toric lens will be out soon, and very excited to hear what the clinical results with my colleagues will be sharing. So we've really spoken about the golden ratio, the beauty of the natural asymmetry out there, whether it's plants, leaves, trees, snails, architecture, art, or intraocular lenses. And the golden ratio really is about achieving continuous range of vision across a broad range of focus distances from far, intermediate to near, optimizing light transmission, reducing issues around contrast sensitivity, improving that mesopic vision and scotopic vision, and importantly, minimizing halos and glare. We're going to hear a lot more about the basic science work and the clinical work, and it's my pleasure to introduce here Dr. Ike Ahmed from Düsseldorf. Please come up to the stage and take us through some of your basic science work and optical work. Thank you very much.